we're going to work through a couple problems with triple integration to find the volume of a solid. So, for part A, identify the convenient innermost integration variable. Alright, for this, what we want to think about is the direction in which we take our last integration. We don't want it to be multiple integrals. If we take it in the z direction, then we have a consistent bottom, but we have a different top equation, right? So we wouldn't want to ideally take it in the z, because then we'd end up with two different integral equations. So instead, we would want y to be our last. And that way, no matter where we go from our projection, right, which in this case is this guy right here, we would have a consistent top, right? In the previous case that we just looked at, if we picked z, right, then we have a consistent lower bound, but we have an inconsistent upper bound, right? We have an upper bound here, we have another one here, right? So we would end up having two different areas of integration on the bottom, and we don't really want that. So ideally, we would pick y. Why? Because if we pick y, then we only have to do one equation, not two. Alright, so let's look at part B. So we can see right here that they picked y as their innermost, which is what we were saying we would do. Then z is the one in the middle, and x is the outermost one. Okay, so let's start by sketching and labeling this. So we got our two outer ones here are going to be what our projection are. So on the z and x-axis, it's always going to be those two outer ones. So let's go ahead and label this as the x-axis and this is the z-axis. And just by looking at this up here, you can tell what the projection is going to look like. It's going to look something like this right here. Okay, well, let's go ahead and draw that. So where does it intersect? Where does this parabola, is what it looks like, intersect the z-axis? Well, if we solve for x equals 0 in this equation, then what do we get for z? We get z equals 1. So we put z equals 1 right here, and then where z equals 0, x is equal to 1. Something. So there we have our intercepts, and there's our parabola, which would keep on going this way. But our region of integration, our projection rather, is right here on the surface, and it says region D. So that's what that is. Okay, so region D is bounded by z equals 1 minus x squared, and by z equals 0 on the lower side. Alright, now we need our x bounds as well. Now, one thing that I would point out about x is on the very outside, right here. Your variable that's on the very outside is going to be only dependent on constants, right? And what do I mean by that? I mean that the equation for the bounds of x is always going to be x on one side and some number on the other. Alright, so let's go into here and draw our bounds on the x. D never goes past x equals -1, and it never goes past x equals 1. Okay, now from this we can write our bounds, right? If we wanted to, we can write our bounds. So x is less than or equal to, greater than or equal to -1, and is less than or equal to 1. And y is greater than or equal to, not y. Z is greater than or equal to 0, and is less than or equal to 1 minus x squared. Alright. Now, just highlight again. Dx, since it's our outermost variable, only be functions of constants, right? The limits for x will only be constants, they won't be equations. Since z is on the inside, we can have an equation of different variables, but not for x. Okay, now this is nice. It's not what the equation, not what the question asks for. The question asks us to express the triple integral as an iterated integral in this order, right? Okay. So let's start that. We got our triple integral right here. And and our equation is just simply fx y z. That's just a placeholder equation. We don't know what the actual equation is in here, but we really don't care for this problem. dy, dz, dx. Make sure you get the order of these correct. Let's start at the outside order. X is the easiest, right? So the lower bound is x equals -1, right? You could also just write this as -1. However, for the purposes of this video, just to keep things clear, do x equals -1. Upper bound is x equals 1. For z, lower bound is z equals 0. Upper bound is z equals 1 minus x squared. Right? So far, all we've done is we've just pointed out where our x bounds are on our graph, x equals -1, all the way to x equals 1. That's where d is between x equals -1 and x equals 1. And then z is between z equals 0. D is between z equals 0 and z equals 1 minus x squared. Okay. Now for the y. Where is y on this graph? Well, it's not on this graph. We have to look back up here to find y. Okay, so we have our projection, right? That ended up being right there. But now let's look and see where the lower upper bounds of y were. And these can be a function of x, x or z, or both, right? Okay, so in this case, we have bound on this side appears to be that face and this face. Right. Okay. These could be planes, right? And they are planes. This is the y equals 0 plane. Right. This one 0 plane. Because it's bounded on the xy plane. This plane right here that's slicing through the object. Okay. This plane right here, what's that? Well, we actually have this nice equation right here that tells us exactly what it is. And we want to rewrite it in terms of y. So y equals 2 minus Okay, now we have the bounds. Y equals 0. Y equals 2 minus z. Fantastic. Alright, so if you're actually writing this out, you don't need to, like I said before, you don't need to take the time to put the x equals or y equals or z equals, but I find that it helps me to actually look for the equations and where they are in the graph. Okay. Now let's look at the second part. Can we set up the triple integral respect to z innermost integration variable? Okay. That's important. Z is our innermost integration variable. So it doesn't say anything about what the other two have to be, the other outer integration variables have to be. But it does say that Z has to be the innermost. Now, if we look back up here, our innermost integration was Y. And Y was not present in our projection. So we know our projection of any triple integral is always going to be the other two outer ones, not the inner one. And in this case, we have sum of x, y, z, d, z, and let's just say it goes dx, dy, right? So these are going to be where our projection is along the x and y. So let's go ahead and sketch that. X, y axis. All right. Let's go back and refer back up to our graph up here. So if we were to look at the xy plane, that's this plane right here. What does our projection look like on that plane? First response would be something like that. Okay, well, we could start with that and see what happens. So, where are our intersections? I think that we found out earlier that this is x equals 1. This is x equals negative. And then down here, what will this be? Okay, so we have z equals 2 minus y. So this intersection right here is equal to 0. Actually, let's rewrite this in terms of y equals 2 minus z, right? When y is equal, sorry, when z is equal to 0, then y is equal to 2. So this intersection is 2 right here. Let's go graph this down here. So yeah, roughly a square. 1. I did it. Up this way because our x-axis is on this side. -1. So let's write our bounds to start with. This is a rectangle. It's pretty obvious. Square root, remember. Pretty obvious where our bounds are going to be. X equals 1, x equals -1, y equals 2 and y equals 0, which is just the x-axis. Okay. And this area right here is our okay. Well, okay, so say that we figure this out. The problem is that once we use this projection and then we try to find upper and lower bounds for that projection, they're not consistent. When we go up this way, right, from that projection, we try to integrate based off of that. We need lower and upper bounds for this region D. But we have two different sets of lower and upper bounds. That means that we need to, we can't integrate the whole region of D over each set of lower and upper bounds. If we did, then that would look something like this, where we did the parabolic one, right? And we added that to sort of wedge-shaped one. In reality, that's not what it is at all. It's sort of the intersection between these two. So instead, we need to come up with two different projections for the two different solids here. So we're going to divide it into two different solids. This solid right here, right, this kind of curved solid, and this arch section right here. Okay. We're looking at this kind of top-down view. We're looking at it kind of top-down. Okay. So instead of having instead of having just D, we have D2. Great. All right. So fortunately, we don't have to write out a triple integral for each one of these. We only have to write one. Well, we don't have to write any integral. We just need to find out what the upper boundaries of each part of the projection are. Okay. Well, what do we want to be our outer boundary, and what do we want to be our inner boundary with respect to x and y? Let's say y is our outer boundary, so no functions for y. Don't want to do this because it ends up splitting it in two when we get to x, and I'll show you that y going from 0 to 2, right? So we go do, right? But then for each of these, right, we need to go in the x direction. We have a lower and upper bound. If that works fine here, 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 and here, and then wait, what do? We kind of got split in half. So we don't want to do any of that. Instead, we use x as our variables. We're going to go from negative 2. And for y ends up being very simple, right? We went from 0 to this equation is, okay, what is that equation? You can kind of guess just by looking at it that this is a parabola where y equals x squared, right? But it's lifted up. So that's our equation for that parabola. We know that this intersects right here at 1, or sorry, at 0, 1, because if we look up here, that's where this plane ends up intersecting this function, right? Because this comes up to a height of 1, this comes out here 2, horizontal plane intersects up here, so halfway in the middle, and that's 1. Sort of just some geometrical reasoning right there. There's probably a better way of doing it, but I don't have time to think about it. Okay. Yeah, that's right. X squared. So 1. Right. Okay. So the upper boundaries is what it asks for. So there's just going to be those numbers right there. All right. Let's see the next one. Identify the convenient innermost integration. All right. Again, we want to be doing this in a direction where we're not going to end up with multiple different equations, right? So if we went in the z direction, obviously that's not going to work because we go out from here and run into 1 on the surface, right? We go up over here and run into another surface. We go over here and run into the surface back here, right? So we have, 3 different equations that we could possibly run into if we do it that way. That's the last one to do. All right. I mean, I guess we could do. You could do y. But the issue with the complexity of that is you're going from one side of the same function to the other side of the same function. And I don't really want to think about that either. So I'm going to say that x is the best direction to go in, because no matter where you go across here, you end up with, you come from this function on this side, go to this function on this side. Gives you 2 nice boundaries. Right? Go from one straight to the other. All right. So I'm going to say x is the best for the lowest because, again, just like the last one, I don't need multiple equations to figure this out. Okay, let's express the triple as an interval in the x, right? So they did do x on the inside. dz dy. Okay, so dz dy is going to be what our projection is based off of, since those are 2 outer ones. So let's go ahead and try our plot for the projection to start with. So we're sketch and okay. So let's do C Y. And we're looking at it from the direction from this way. Right? We're looking at it from this way. So what is it going to look like? It should just look like a parabola, right? Okay, but where are the intersections? Right? We're looking at sort of this cutout right here. Right? Where are the intersections? What's this? What's this? What's this? So let's start this time. This parabola right here, this parabola surface is given by this equation. So we can solve for where y is equal to 0, which gives us c equals 4. So put this up here at 4. And down here, where y is equal to 0, that gives, where z is equal to 0, that gives us a 0 equals 4 minus y squared. So we have squared equals 4, so it's 2. Right, so intersection 2, 2, 3. And the function of this parabola is just going to be this function right here, because this is a function relying on y and z. So z equals 4 minus y squared. Right. That's my upper bound. My lower bound is going to be, it's just going to be z equals 0. Okay, and it's okay that we have a functional variable because the z is not the it's okay that we have z as a function of another variable because z is not our outermost variable. So our outermost variable is y, and let's look at the balance for y. Balance for y look like y equals -2, right? Because this was -2, this was 2, and then y equals 2. Great. This is D, and I think we're good to go ahead. Actually, we gotta label C equals 0. Gotta label everything. Okay. And we're good to start writing, right? X, D, Z, and D, Y. Okay, well, let's start from the outside and work in, because that's the easiest way to do it. Y equals -2. Actually, this time I'm gonna write it with, actually, I'm gonna keep writing it with in the equation form. Y equals -2, y equals 2. Then we have, for dz, we have z equals 0, right? That's our lower bound. And then our upper bound is this parabola right here as far as z goes, right? We're going this way. Okay, upper bound is z equals 4 minus y squared. And then we have whatever our x ends up being. Okay, now because we got to the innermost one, it's time to jump from our projection back over to our 3D. So x goes from this wall right here all the way over to this one. Actually, since this one's on the negative side of x, it would start here. This would be the lower bound, and it would come this way over to the upper bound right here. All right. Well, it would have to be rewritten so that it's in terms each of these equations, because these are equations for both of those sides here. Clear this up. These are equations for both of those sides. They need to be rewritten in terms of x, because this needs to be x equals something, right? So this turns into x equals z minus 4. This turns into x equals 3 minus z. Okay. That's our lower bound. Lower bound is going to be this one right here. Upper bound, so it's right in here. See the minus 4. Our upper bound is this guy right here. So that's 4 minus z. Okay. And that's it for part B. Let's move on to the next part. This is should be C. Can we set up a triple integral with respect to y? Yeah, I think that we can, but let's look at what that would look like. Because we would need the projection, and since it's with respect to y, and that's our innermost variable, then the projection is going to be on the xz plane, as we explained before. Okay, so xz plane cuts through this solid. If you were to do a projection of the xz plane, then it all falls within this right here, right? That's if you're viewing from this angle, that's the profile that you're going to see. So let's go ahead and figure out what these intersections are going to be, and then we can draw it out. So this intersection up here is going to be 4. We already figured that out, right? It was our top here, right? And since these are linear and there's no slope either of these, there's just a up and down movement of 4, right? We know that this is a 1/1 slope. So this also has to be 4. This will be -4. Right? Okay. So let's go down to our graph then. Z this one 0, 4, 4, 0, -4, 0. Great. And our balance. So here's where we need to decide which is going to be our outermost variable. If we make x our outermost variable, then as we go across from x, we run into 2 different functions. And that's not what we want. That means that we're going to have to make 2 different functions. And we'd rather not do that. So instead, we're going to make z, right? Z our outermost. And so as we go along z, we have a lower bound out here, upper bound out here for x. And we only have an equation we have to make because we have one set of lower and upper bounds. So z is the simplest one to work on because it's our upper bound. Sorry, not our upper bound, our outside, our outermost variable. So this is z equals 4, this is z equals 0. So z ranges from 0 to 4. X ranges from, well, what's the equation of this line? Let's go back up here. Yeah, it's this guy right here. X equals, actually no, it's this one over here because it's something. On the negative side, x equals z minus 4. X equals z minus 4. Another one is x equals 4 minus z. Okay, lower bound is z minus 4. Upper bound is 4 minus z. Okay, that answered the question. All right, well, if this helped you out, please leave a like and let me know what else you would like me to work on. And I'll do my best to make a video or answer your questions. Thanks for watching.